Good morning, gentlemen. Today is Monday, May the 11th, and today we are going to continue our discussion of waves. Now, a couple of days ago, we talked about what happens to a wave when it strikes the boundary between two different media. The examples that we were talking about at that point were springs, and we said that if you send a wave down the length of a spring and it strikes the wall, it'll be mostly reflected back. But that's not always the case. Sometimes waves are not reflected, but rather refracted, which means that the second medium is absorbing those waves, taking and having the energy of the wave transferred into it. All right. And so this process is what we call refraction. Now, when a wave strikes the boundary between two different media, it can either be 100% reflected, it can be 100% refracted, it can be some combination of both, or it can be some combination of both, and there can be some absorption. All right. So we're going to cover most of those options over the course of the next few lessons. But for today, let's just talk about what happens when a wave actually travels between two media, from the spring to the wall, from the ocean to the sand, right? When a wave crashes on the beach, if you're standing on the beach, you can feel the smack of the wave on the sand because the wave actually continues right through the sand. So when a wave passes,
It's 7 o'clock.
Thank you, Jesus. When a wave passes between media, it changes its velocity. But because the wave in the new medium is generated by the wave in the old medium, its frequency remains constant. All right, now think about that. Remember the rule F equals frequency times wavelength. All right. So when a wave passes between media, it changes its velocity. It travels at a different speed in different media. And so because the wave in the new medium is generated by the wave in the old medium, the frequency has to stay the same. Therefore, the wavelength must change. And this causes a change in the direction of the wave. All right. That's a mouthful. All right, that's a little bit to chew on. So take a few minutes and read through this a couple of times and make sure that you understand what we're saying here based on the velocity formula that we've talked about before. Now, that leads us to a discussion of what happens to the wave, right? If the velocity is changing, but the frequency remains the same and the wavelength changes, it changes direction. So let's put together a little puzzle here. This is not quite how I intended this to work out, but so the thin line here is going to be the normal line, and the darker line is going to represent a boundary between two different media. This red vector that just popped in is going to be an incident ray, and the second red vector is going to be what we call the refracted ray. Again, we're going to do the same thing on the right-hand side. Now that's the incident ray, but notice in this case, the refracted ray is not moving in the same direction that it does on the one on the left. So the question here is, what exactly is the difference between all of these things? Well, okay, let's have a look at this, shall we? First, let's change the color of the ink. And so this is the normal. This is angle I, the incident angle, all right, the angle in here. This is angle R, which is the angle of refraction. So what's the deal here? Well, this thing right here represents the boundary. And the boundary itself is between, in this case, a less dense medium and a more dense medium. So for example, we might be traveling between air and glass or air and water, all right? But it has to do with the density here. And notice that in this case, the angle of incidence is greater than the angle of refraction when we travel from less dense to more dense. Now, on the other hand, we've got our normal here. We've got a boundary here. But in this case, I've got a more dense medium and a less dense medium, all right? But notice that they've reversed positions, dense and dense. So more dense and less dense. In this case, maybe we're traveling, from glass to air, okay? Or, from water to air or something along those lines. So in any event, the angle of incidence now, all right, which is essentially equal to the angle of incidence that I showed you in the first case, is now much smaller than the angle of refraction here, because we're traveling from the more dense medium to the less dense medium. Now, mathematically, at least when we're talking about light, there are some constants that go along with this, but we're going to hold off for a couple of days until we get to a specific discussion of light. This happens with sound, it happens with light, it happens with all sorts of other electromagnetic rays, and any kind of wave will or can be refracted. Okay. That leads us to the last slide here. And this is essentially just two YouTube videos done by the same woman who did the reflection video that you watched on Friday or Thursday, whenever that was. And it's essentially a two-part video. Both of the parts cover ideas of refraction and show you these things in animation form that I just don't have the talent or the ability to do on these little podcasts here. So in any event, happy Monday. Have yourself a lovely, lovely day, and I will see you tomorrow.